Simple harmonic motion, 2017 higher level, question 6. So as always, when we're looking at exam questions in physics, it's always a problem because there's quite a lot of reading in one question alone and no parts labelled 1, 2, 3, 4, 5, 6. So the biggest advice I can always give to you when doing exam questions is to actually number the parts. So here we can see in a bungee jump, Henry falls while attached to an elastic cord. When the cord stops Henry's fall, he then oscillates up and down. During the bungee jump, gravitational potential energy is converted into kinetic energy and then into elastic potential energy. So state the principle of conservation of energy then is the first part of the question. So we're going to number all of these parts first of all, right? So we're going to call that 1 or part 1. We then have to derive the expression. So we'll say that's part 2. We have the cord is 32 metres long and we have to calculate his speed when he has fallen. So that's going to be part 3. We then have a stretched elastic cord obeys Hooke's law, state Hooke's law. So that's going to be part 4. We then have to calculate the length that the cord would have if Henry was suspended at rest. So we're going to say that's part 5. After the fall, he oscillates up and down, and we have to calculate his maximum acceleration and his period of oscillation. So that's going to be part 6. And then we have to draw a diagram, which is going to be part 7. Now, obviously, there's 2 parts within part 6 as well. So if you want to number them 1, 2, 3, 4, 5, 6, or A, B, C, D, E, it's up to yourself, whatever you call them, okay? So we're going to start with part 1 there. So the first thing we were asked to do there was to state the principle of conservation of energy. And quite a few of you actually kind of gave an attempt at this. So I was actually surprised that you didn't know this off by heart. This should be one of the easiest definitions that you learn. If you are not learning your definitions, it's going to be a problem. So again, go back to your revision sheets that I've given you where it has every single definition. Go to Quizlet, practice testing yourself on your definitions. But it's really, really important that we know our definitions word for word. It's a definition for a reason. It's not just in your own words, explain what you think this means. There is a set definition for this. So when we're asked to state the principle of conservation of energy, I'm just going to shorten that to principle of conservation of energy. Then what we need to state is that energy cannot be created or destroyed right? And that's what they accepted in the Leaving Cert for 3 marks. But I would prefer for you to state energy cannot be created or destroyed. It can only be transformed from one to another. Okay, so as I said, most of the 3 marks are just going for energy cannot be created or destroyed. Okay, so it's just important to note that obviously we can see here in the question, during the bungee jump, gravitational potential energy is converted into kinetic energy and then into elastic potential energy. So we're not destroying the gravitational potential energy, it's being transformed into kinetic energy, and then that kinetic energy is being transformed into elastic potential energy, okay? So the next thing we were asked to do then was to derive the expression. Okay, so in other words, derive means proof. And this was page 69 in your books. And we have to derive that v squared is equal to u squared plus 2as. So like our proofs and trigs, we can only use the formulas that come before the one that we are trying to prove. And therefore they are set proofs when we lay them out. So any of the proofs that I've given to you, and again, all your proofs are on that proofs handout that's in your Edmodo folder for your revision for Leaving Cert, and you'll have all of the proofs laid out in that document. So again, please download that document. Normally I'll give you hard copies of these. If we're back in school before the end of the year, you'll get hard copies of any of these revision documents. But if not, they're all in your Edmodo folder, okay? So if you do have a printer at home, try and print them yourself. If not, download them so you can go through them on your computer, okay? So what comes before v squared equals u squared plus 2as? Well, we can see v equals u plus at and s equals ut plus a half at squared. So we're going to use these equations to end up with this third linear equation of motion, okay? And therefore we're going to start with, we know that v is equal to u plus at. Now I want v squared here, so I'm going to square both sides. Now please be careful, if you're squaring both sides, that means you're squaring the left and you're squaring the right. So that gives me v squared is equal to u squared plus 2uat plus at to be squared, which is a squared t squared. Okay, so again, it's everything in the first bracket there by itself. So u plus at by u plus at. Okay, so I'll murder you if you can't square out your brackets now at this stage. Okay, so it's really, really important to be able to square those brackets out properly. So if I look at that, I'm now really happy because I have a v squared and I have a u squared and I have a 2 and I have an a. So I don't want this u and I don't want this t. Okay, so I'm just going to undo that to get rid of it. So we need to get rid of that ut and we need to get rid of the a squared t squared. But what I can see is that I have something common. And what do I have common? Well, I have an a common here and an a common here. But I need that 2, so I'm actually going to take out 2a as being common, even though there is no 2 in the a squared t squared. So of course, if I take out 2a as being common, well, that leaves me with ut. If I take out a 2 when there is no 2, well, then that leaves me with a half, because 2 times a half is 1. And if I take out an a, I'm left with 1a, and I'm left with a t squared. Now again, if we're on page 50 in our maths tables, what we can see then is this ut plus a half at squared is equal to s. So we have s equals ut plus a half at squared. And because it becomes before v squared equals u squared plus 2as, then I'm allowed to use that. If it comes after it, I'm not allowed to use it. And there we go, we have our proof out. Okay, so in terms of breakdowns of marks, you were getting 3 marks for stating v is equal to u plus at. Just put that back up there. So that was 3 marks. We then had to square both sides, which was 3 marks. Squaring it out properly, 3 marks. And then letting s equals ut plus a half at squared and getting out v squared equals u squared plus 2as was 3 marks. So there was 12 marks in total for that derivation. Okay, so the next thing we want to do then is look at part 3, where we have the cord is 32 meters long and Henry has a mass of 60 kilograms. He falls from rest. Okay, so just underline falling from rest. That means his initial velocity is 0. And we have to calculate his speed when he has fallen 16 meters. So if we go on to the next page there and we list out all of those values that are given to us. So in the question, he's falling from rest, so therefore his initial velocity is 0 meters per second. His mass is 60 kilograms, and we want to find his final velocity when he has fallen 16 meters. Okay, now if we think about that, right, here he is standing on top of the bridge. Right, he has this cord attached to him. When he jumps, at some point he has fallen 16 meters and his string is attached to the top of the building. But as he's falling, there's no tension in the string at this point in the elastic cord, okay? So therefore, if the elastic cord has no tension in it, that means he is actually in a state of free fall. And if he's in a state of free fall, that means his acceleration is acceleration due to gravity, which is 9.8 meters per second squared. So therefore, the mass is irrelevant for this part of the question, because we've just proven that v squared equals u squared plus 2as. So it was almost a hint to you that you needed to use that for this question. So if I sub in there, v squared is equal to u squared plus 2as, then v is going to be the square root of 2 times 9.8 times 16. And therefore that gives us a value of gravity of 17.71 meters per second. Okay, And again, rule of thumb normally in physics for Irish physics is, number of significant figures in the question, and all the numbers and significant figures in this question are kind of to two significant figures. So you could give that as 17.7 even as your answer, or I wouldn't round it to 18. I would definitely keep it normally to correct it 1 or 2 decimal places is the rule of thumb in Ireland. We're not too fussed on significant figures in physics in Ireland. Okay. In the next part of the question, then, if I go back, part 4, a stretched elastic cord obeys Hooke's law, and the weight attached to the cord oscillates with simple harmonic motion. State Hooke's law and what is meant by simple harmonic motion. Now, just to go back to part 3 there, you might kind of go, well, how do we know that he was in a state of free fall? Well, the distance he'd fallen is only 16 metres and the cord is 32 metres long. So therefore he hasn't actually even reached the length of the cord yet. So there's definitely no tension in that cord. Okay, so he is in a state of free fall. So for the next part of the question, we have to state Hooke's law. Okay, so what is Hooke's law? So for Hooke's law, we would say the restoring force is directly proportional to the displacement. Okay, and again, you can say F is the restoring force and S is equal to the displacement. So again, if you're using formulas or anything like that, you should always state the notation, okay? Or in words, we would say the restoring force is directly proportional to the displacement and in the opposite direction, okay? So the next part of the question says what's meant by simple harmonic motion. So again, simple harmonic motion is that the acceleration is directly proportional to the displacement. So again, we would have to state A is acceleration and S is displacement. And again, if we were looking at it in terms of words, we could of course say that the acceleration is directly proportional to its distance from a fixed point on its path and is always directed towards that point. Okay, so again, you would be better off always saying F is proportional to S rather than F is equal to minus KS, because in terms of defining Hooke's law, it is restoring force is proportional to displacement. So, you just be careful with sometimes writing down the formulas that are in your tables literally if it is somebody's law like Schnell's law or Boyle's law or Hooke's law, okay? And again, same with the simple harmonic motion there. Obviously, A equals minus omega squared S is the formula that's going to be in your tables. But again, for defining simple harmonic motion, we tend to say acceleration is directly proportional to the displacement. So in terms of marks for that question, there was 3 marks for each of the definitions. Okay, so if we go back to the next part of the question, is a calculation, part 5, and we have to find the length of the cord that would calculate the length the cord would have if Henry is suspended at rest. So Henry is suspended at rest and we're looking for the length of the cord, and we're given the elastic constant here in the question, okay? So let's list all the values we have. So we know that if we're looking at the elastic constant, well, we're going to be using F is equal to minus KS is our Hooke's law. And again, the values that we have are the elastic constant, which is 250 Newton per meter. We know that the distance is what we are trying to find. Now, you have to be careful here because S refers to, like, if we think about there's Henry falling, okay? Well, what happens is the cord is 32 metres long, But because it's elasticated, it's going to stretch beyond its natural length. So therefore the extension is S when we're doing Hooke's law. So if we're looking at the length at the end, because we're asked for the length of the cord, it must be the two combined together. So quite a few of you actually missed that and just gave me S, the distance, okay, the extension. Okay, so I'm looking for S. So if I'm looking for S, well, I need to know F, but I haven't been given a force in the question. So how do we normally find F? Well, we know that F is equal to mass times acceleration, and I know my mass is 60 kilograms. And the acceleration then, again, if he is suspended at rest, so calculate the length the cord would have if he's suspended at rest. So again, our acceleration is going to be 9.8 meters per second squared. So F equals ma. Okay, so then if we put our values in here, we have our mass times our acceleration is equal to our constant, which is 250 times S. And S, the negative value for that means it's just going back in the opposite direction. Okay, so for the purpose of this, we can just say S is equal to 60 times 9.8 divided by 250, which gives us a extension of 2.352 meters. So this is the stretching on the string. So this is our extension. Okay, and therefore, because we're looking for the length of the cord when he's just suspended at rest, so in other words, he's stretching the string, he's just about to go shooting back up. So therefore we have the length of the cord is 32 plus the extension 2.352, which gives us a length then of 34.35 meters. And a lot of you had given me the answer as 2.352 meters, okay? So for that question, we were getting 3 marks for our Hooke's law formula. We were getting 3 marks for substitution and 3 marks for the answer. Now, a lot of you got the 9 marks and then -1 because that year they were quite nice and they actually only deducted 1 mark if your answer was left as S is equal to 2.35 meters, okay? So the next part of the question then, if we go back, is part 6. We have to calculate the maximum acceleration as he oscillates and his period of oscillation. So at the end of the fall, Henry oscillates with simple harmonic motion and the maximum displacement from his rest position is 1.2 meters, okay? So that's the maximum displacement from his rest position is 1.2 meters. So this is going to be part 6. Yeah, part 6. Okay, so what are we given? Well, maximum acceleration is A equals minus omega squared S, which is our simple harmonic motion. Now, we don't have the constant here in this question. We do have the displacement. We're told the maximum displacement for the maximum acceleration is 1.2 meters. And if I'm looking for A, well, I need to know what omega squared is. Now, we have to remember that we did a little derivation on F equals minus Ks, and F is equal to MA, and therefore A is equal to minus K over M, and of course simple harmonic motion we've just written down as minus omega squared S, so therefore that implies that omega squared is equal to K over M, and we know that K is the elastic constant which we were told was 250 Newton per meter, and M is his mass, which is 60 kilograms. So you weren't asked to do that derivation, but you are needed to know that relationship, okay? So therefore, if I sub in now, I'm looking for A, I have minus omega squared, where that's going to be K, 250 over M, which is 60, times s, which is 1.2. And then that gives me my acceleration is so it's minus 5 meters per second squared. Now, it didn't say anything about the minus, an omission for the minus in this question. I think I did take -1 off you, but really I suppose if I'm looking back at 2009 in the high level marking scheme there for question 12A, there's a similar question there and they don't have the minus in the answer, okay? So therefore, you know, you weren't being penalised for using A as the absolute value or A as being the minus. The minus only really tells us that the direction is in the opposite direction to the displacement, okay? So if you want to give yourself that 1 mark back, you can. I suppose I was just taking it literally from the marking scheme in that particular year. That's not to say from year to year that they don't change their marking scheme, but I suppose even in the textbook we don't really normally bother with the minus sign in Hooke's law and simple harmonic motion. So you can start, the minus is because acceleration is a vector and it's all to do with the direction, but we can take 5 meters per second squared as our actual answer, okay? So you can give yourself back your mark, 1 mark there that I had taken away from you, okay? So if we're looking at the marks for that part, then we had 3 for getting this relationship here, and that comes up quite a bit, so that's really, really important. So do star that, your relationship between Hooke's law and simple harmonic motion, okay? And then our A equals minus omega squared s was 3 marks. Then we had 3 marks for substitution and the answer. So that was the first bit within it. I'm just going to call it A, even though it's part 1 in the question. And then part 2 is the period of oscillation. So period of oscillation with simple harmonic motion is 2 pi over our omega. So therefore we have our omega is going to be the square root of k over m. So when we're subbing in here, we have 2 pi over the square root of k was 250 over m, which is 60. So then when I sub that in, I end up with, sorry, I don't know what I've missed there now. I'll go back over B there just in case, because the recording had stopped. So our period for oscillation is 2 pi over omega. Omega squared we know is k over m, so therefore omega is the square root of k over m. And k was 250 and m was 60 as above, okay? So therefore we have 2 pi divided by the square root of 250 over 60, which is 3.08 seconds, okay? And again, breakdown of marks for that was 3 for our formula and 3 for the answer. Okay, so you're always getting marks for your formula, so always making sure you're going to your tables and you're finding these equations, because really, really important that you're going to write them down and then use them, which of course is page 55 in your maths tables, okay? Now, the last part of the question then is the diagram. What did I call that? So it's part 7. And the diagram was when Henry reaches his lowest point, what is happening to him? Okay, so here's Henry. Yay, screaming down, okay? He's going to be attached by the cord, okay? And therefore at his lowest point, what we have is 2 forces, okay? So we're going to have weight acting down, but because he's at his lowest point, that means that he's about to spring back up. So that means that the cord has been maximized in terms of its extension, and therefore it's going to have tension acting up away from him. So what you should notice is that the tension is greater than the weight, because he's about to fling back up, okay? And again, you were getting 5 marks for this question, so 3 for showing 1 down and 2 for showing the other force, but 1 had to be larger, so it was 5 marks in total for that. Some of you were saying that they were equal and opposite, which would mean that he'd be at rest, okay? But he's literally about to spring back up. So the tension in that string is going to be huge, so that it's his restoring force. So you'd get -1 for each incorrect arrow there. So mostly had the 2 correct arrows labelled correctly, but just missed the fact that tension was going to be greater. Okay? Any issues, just send me a text and I'll have a look and see what you aren't sure of.